Okay, well, nice to see everybody. It's exam week, very exciting. So the plan for today is I just want to wrap up a couple of examples we didn't get to on this worksheet last time. So this is worksheet 10, where we did some existence proofs and then we started some disproof a little bit. So I want to do a couple more examples of disproof, and then we'll spend the rest of the time talking about the exam. So if you have any questions about the exam, please just hold on to them for a few minutes until we kind of wrap this sheet up, and then I'm happy to answer any questions that you might have for the exam. So just keep in mind, there was a homework assignment that was not being collected that is due this evening. So I will put up solutions to that so you can check your work on that one. The previous homework assignment 4 is still in the process of being graded. I will put solutions to that homework assignment up as well, so at least you can check your work with that answer key. Okay, so last time, let's see, we did a bunch of these, and from my recollection, we did 3A and 3B, and we didn't get through anything else on this page. So just to kind of quickly recap what we did on this sheet is first we talked about proving existence statements like this. And so to prove an existence statement, it's actually quite simple compared to some of the other proofs, in the sense that we just need to give one example, either concrete or show that one exists, doing it non-constructively. So to prove an existence statement, we just need to construct one such statement. To prove a for all statement, that's what we've been doing all semester. Those can be quite tricky. But if you need to show that it works for just one value, then that's all you need to construct. When it comes to disproof, we'll see that the reverse is true. So let me take a look at, say, C. I don't think we did this one. Yeah. So C is a statement. I just kind of pulled it down here so we have a little bit more space, which says, okay, we've got two sets, A and B. The claim here is that the power set of the union of A and B is equal to the union of the power sets of A and B. So the question here is prove or disprove this. And so if we wanted to prove this, then we would need to show that this is true for all possible sets A and B. So this is actually this is a universally quantified statement, in the sense that it's really saying for all sets A and B, this equality has to hold. So if we want to prove this, we need to prove it for all such things. I'll just say that this statement is actually false. So let's focus on kind of disproving this. And so the way that we disprove a universally quantified statement, which is something like for all elements X that are in some set, some statement, I'll call it Q of X, is true, then what we want to do is show that its negation is true. And if the negation of this is true, then the original statement must be false. So that's how we prove things are false, is we show that their negation is true. Or at least that's one way that we can do it. So if I want to disprove a universally quantified statement, then I negate it. Sorry, that's my cat. She's okay. Thanks for the concern. Then I want to negate this universally quantified statement, which means we change the quantifier to an existential quantifier, and we negate the original statement. So in other words, we are going to prove this. So in other words, we need to prove an existence statement. So negating this statement, this universally quantified statement, is equivalent to proving an existence statement, which is what we focused on last time. So to kind of summarize that, kind of over here, if we want to disprove a for all statement, then we negate it like we did over here, and we get an existence statement. And so in order to prove that the existence statement is true, then we just need to apply one such example. So in this case, if we want to show that this statement is wrong, then what we need to do is we need to show one concrete example of sets A and B such that the negation of the original statement is true. And for us, if we were to negate this, it's the same thing as saying the power set of A union B is not equal to the power set of A union the power set of B. So maybe logically that might have been a clear connection to you, but maybe not. So the point here is, if we want to negate this for all statement, then we need to find sets A and B that exist that are going to make this not true. So that was a long build-up. Does anyone, while I was building up, come up with sets A and B that are going to violate this? You can chat them in if you've got an idea.
Does one of them involve just being the null set?
Yeah, I mean, there might be all sorts of contradictions. So if you want one of them to be the empty set, and then what do you want B to be?
No, I think I just disproved my own idea.
Okay.
Yep.
But I think this is the right idea, in that, like, the empty set is like the simplest, one of the simplest sets that you can think of. So I don't think you want to start by thinking about, like, what are the most complicated sets A and B, but rather, like, what are the most simple sets A and B that might satisfy this? Where? Any thoughts? I don't want to do this myself, but I do want to have some time for reviewing exams. So if you've got one, please don't be shy.
Wouldn't it be like anything? Okay, could, like, if you took the null set in 1, 2, 3, wouldn't that still be, or actually you have to have something with the null set in it, right? Okay, what if we took A is equal to 1, 2, 3, and B is equal to, sorry, I'm trying to work through to give you something.
Okay, no, that's fine. I mean, this is how we try it, right? We try something out, and maybe we'll get lucky and it works. But even if it doesn't work, that might be a hint at, like, we might see why that didn't work and be able to correct it. So,
Well, the idea is that if the power, I was confused at first because I was mixing the power set with like probability because of my other classes.
yes, no, we're not doing probabilities here.
But if the idea is if we take like two different sets and you do the power set of like those two sets combined, we'd only have a certain amount of those two sets instead of taking them separately, if that makes sense.
Yeah.
So there should be multiple ones that don't work. I'm just trying to think through it.
So let's try, say, that's about the easiest set that I can think of. What's maybe the second easiest set that you can think of? That's a set that has no elements. What might be the next basic set to think about?
Set with just one element,
Yeah.
like the number one.
Oh yeah, and we'll pick one, sure. Let's just see what happens here. So A, so first of all, the power set of A, in this case, would just be the set that contains the empty set and the set of the empty set. And the power set of B, in this case, would be the empty set and the set itself. So it doesn't look all that unlike the previous one. And so from this, we can calculate the union of the power sets of both of these. So that would be the union of those two sets. So I would get empty set, the set containing the empty set, and the set containing 1. Any questions about that so far? So that was kind of over here. We have the definition of power sets, and now we're just using definition of union of two sets. And let's kind of compare that to the other side, which is what would we get here. And so if I take A union B, I would just get the set 1 back, right? Since set A doesn't have anything and set B just has 1. This is Onyx. She is a 17-year-old cat that has pins in her legs because she was in an accident as a kitten. She got caught in a fan belt of a car, and she's had 17 years of a happy life since then. So she's making a lot of noise right now. Okay, Onyx, relax. Sorry. Okay, so we're working with these sets A and B. So we had A was the empty set, B was the set that contains just one element. So the union of those two sets would be all of the elements that are either in A or B, which is just that one unit A, that one element A. And so if I took the power set of A union B, notice A union B is exactly the same as the set B, right? So I would just get the power set, excuse me, that would contain, well, all power sets have the empty set. And all power sets also contain the original set, And that's all that we have there. And so now I think we've got a counterexample, right? Since these two sets are not equal to each other because this element is in the top set, but it's not in the bottom set. And I actually think it would be hard to come up with an example where this would work. I think just about any examples that you would have thought about probably would have not worked. This is definitely not a true statement. So my suggestion to you is if you're kind of not sure whether something is even true or false to begin with, a good first step might just be taking a couple of really simple examples and seeing if it seems to work or not. If it doesn't work, then you're done. If it does work, then you might want to pick up on a pattern and say like, oh, okay, does this seem like it's going to work for all such values? Or does this help me see that there might be a special situation where it wouldn't work? But you know, the best access point for these sorts of problems is to just start experimenting with different things. And so just to kind of organize this more clearly, since we kind of had a stream of consciousness going on here, the proof for this one would be, we just need to give this concrete example. So it would be that A equal the empty set and B equal the set that contains just the unit 1. Then we can say the power set of A union B. In that case, we found that it was empty set, the set containing the empty set, and the set containing 1. Is that how we did it? Sorry. Right, so we showed that the power set of A union B was just the empty set and the set 1. Okay, and that comes from the fact that the union of those two sets is just 1. That's it, okay? So just like existence proofs, you just need to show, here's my example, and then show the reader that, look, this example, here's the work that shows that it doesn't match up.
Can I ask you a question about that?
Yeah.
So are we saying that A is the empty set or that A contains the empty set?
We are saying that A is the empty set. So there is a difference between this and that. So you just want to be careful. This is a set that contains nothing in it. Whereas this is the set that contains one thing. The one thing that it contains is the empty set.
I thought the power set of the empty set was just an empty set. I didn't, yeah, that's the part that was confusing me.
The power set of the empty set would be the empty set, and the would be the set containing the empty set. I should say that, yes. Did I not say that somewhere? Ah, I see. So in this case, sorry, if A is the empty set, the power set of A, you're right. That was a very calculated error on my part. Right? The power set would just be the set containing the empty set. Sorry.
And does that change the union?
It does, yeah. That actually makes this not a counter example. Since this is actually not going to be in the union of the power sets. So yeah, so making this correction over here, thank you, Wilfred. The power set of A is just contains one element. If A is the empty set, the power set of A is the set containing the empty set, and that's it. And so now when we take the union of this and this, we would actually just get the empty set and the set containing one, which is exactly the same as what we have up here. That one didn't work, but there is a counter example that will work. Let's change A. I think B is fine. You caught the mistake, Wilfred. Do you have a suggestion that you want to use for A?
I think if we made A the set containing the empty set.
We can make A the set containing the empty set. Why don't we pick, let's pick examples that don't involve the empty set. So like, let's try and pick the simplest maybe example. So set B equals 1, that's a really simple set. Let's try and pick something just as simple for A. So we'll pick it to be a set that contains one element. That's a good plan, but let's not make it the empty set.
If it did contain the empty set though, like the set of the empty set, we wouldn't have to change anything of what we just worked through, right?
Yeah, but let's try like 2 and see how this works with 2. Rather than pick a more abstract set like the set containing the empty set or something like that. And let's see if that works. So if we pick A to be 2, then the union of these two sets would be what?
Just 1 and 2.
Yep, would be the set containing 1, 2. So then the power set of the set containing 1, 2 would be the set containing the empty set, the singleton 1, the singleton 2, and the set 1, 2. Right, so what we're saying is if this is my set, then this is the corresponding power set of this. And we also have that the power set for A here is just the set containing the empty set and the set containing 2. And the same sort of thing holds for B. B just contains the empty set and the set containing 1. So if I take the union of the power sets of A and B, then what would I get? Sorry, that's messy.
We get everything but the set 1, 2.
That's right. I would get the empty set once. I mean, it appears in both of those. So that would be in the union of those two sets. I would get 2. I would get the set containing 1, and that would be it. And so now I can compare this to what we had up top, where the power set of A union B contained this element over here, which is not contained in the union of the two power sets. So there is nothing wrong with trial and error when it comes to these sorts of things. In fact, that's kind of the best way to pick up on some patterns when you're trying to do these anyway. Okay, any questions about that? And so kind of the big takeaway here again is if you want to disprove a for all statement, then you need to prove an existence statement. Basically, you need to show that there are two values or however many things. You need to show that there's one example that makes the claim false. That's the main goal here. Okay, and if we have a conditional statement, it follows very much the same way. So question F, right? This is a conditional statement. And the question here, again, is, well, let's prove or disprove this. And this is a conditional statement. So the way that we can disprove a conditional statement is we find an example that makes the hypothesis true, but the conclusion wrong. So it's essentially the same exact thing that we just did. Conditional statements are actually, it's assumed that they're universally quantified statements. So it's the same way. We want to find one example that makes the hypothesis true, but makes the conclusion false. So in this case, our statement is P implies Q, where we've got P is the statement that A and B are sets. And the conclusion, Q here, is this statement about the cardinalities of these sets. Okay, and again, that's called the cardinality. So kind of the hypothesis here is there's really not much here, right? It's just saying we need to find sets A and B that are going to violate statement Q. And if we can, that's going to be our proof. And if we can't, then we might want to think about, well, maybe this statement is actually true, and let's try and prove it.
I think for an sets to try, just set A equal to the set 1 and 2 and B equal to the set 2 and 3. I think that would work.
Okay, so let's check it out. So the suggestion here is let's set A, what'd you say, Brandon, was 1, 2?
1 and 2, and then B was 2 and 3.
Okay, so then if this is the case, then first of all, note that the union here would be the set 1, 2, 3, So the cardinality of this set is equal to 3. But if we just took the two cardinalities and added them together, we would get 4. So we just found here are two sets A and B that don't satisfy this property. So that's our disproof right there. Good. And basically the key here is you just need to pick two sets whose intersection is not the empty set, and it would work out. So these two types of disproof, a for all statement or a conditional statement, they're basically the same type of proof. For all statements and are conditional statements in disguise and vice versa. So the idea here again is still come up with one counterexample and you're done. Let me say that if we want to disprove an existence statement, that's a bit trickier. And so just to kind of point out something, when we're doing proof of an existence statement, if we can construct one example that satisfies that, we're done. In order to prove a for all statement, okay, we recognize that it's a conditional statement, and then we can use direct proof, contrapositive, contradiction, any of these other proof techniques. But let me just say it's more complicated. You would need to use some proof technique. And when we're doing disproof, let me just say to disprove a for all statement, we just need one counterexample. To disprove a for all statement, excuse me, to disprove an existence statement, we're going to have to prove a for all statement is true. So it's a little bit harder. And so let's kind of see how that looks. With E. Okay, so here is an existence statement, and this statement is actually not correct. There are no such primes that are going to give me a difference of 97. And so the logic here as to why are we going to disprove this by proving a for all statement is this original statement, I'll just call it P, is saying there exists primes P and Q such that P minus Q is equal to 97. And if we think this is false, then what we are going to do is we are going to show that its negation is true, which is equivalent to therefore proving that P is false. And when we negate a statement like there exists primes P and Q such that P minus Q is 97, the way that we negate existential statements, existential quantifiers, is we change it to a for all. So we're going to say for all primes, P and Q, it follows that P minus Q is not equal to 97. So when we negate an existential statement like this one, an existential quantifier, we change it to universal quantifier, and then we negate the original statement. So hopefully it makes sense that if we want to disprove that there are prime numbers P and Q, that this is true, that's equivalent to saying that no matter what two prime numbers I pick, this can't be true. And that's a bit harder to show, right? I can't prove this with just one counter example. So basically, we need to show that if P and Q are primes, then there's no way that their difference would give me 97. And this is something that we can certainly prove, but the point here is that in order to disprove an existential statement, we're going to have to prove a universal statement. And that's what's summarized in this last bullet over here. Any questions about that? Okay, then I will just leave this part E as it is here. And if you want to try and work that up on your own time, you're definitely welcome to do so. And I can put up the solutions for this. But again, just to kind of take away about proof and disproof, you know, we started the semester with these types of problems, proving conditional statements, just to get a good rundown of what we've been doing up to this point. So we kind of started with problems like this, proving conditional statements. Then we talked about, well, sometimes not all things are conditional statements. So to prove an existence statement, easy peasy, just give one example. And then from this, we have the negation side of this, which is disproof. So disproving a conditional statement is not too bad. We just need to prove one bad counter example. Disproving an existence statement is not easy. That means we need to prove that a for all statement is true. Okay, so I'll kind of stop here and let you guys take some control over this. As far as the sheet goes, let me just do some bookkeeping here. We've done this one today, and we did this one today, and this one we kind of started. And I will put up the finished proof for that. Let me just say, this one you can skip as far as I wouldn't ask you something that difficult on the exam, but I think this is certainly a good one to practice. Practice finishing up this one would be good, and we haven't talked about this one at all. Think about whether or not that's true and how you might want to prove that. And I can put up solutions to this, or we can talk about it now if you want, but I'll just stop and give us a chance to talk about anything about the exam.
I had a quick question about example F that we just went over.
Yeah.
How did we get 3 and 4? Like when we were doing the proof, like for the sets, like how did we get?
Yeah, so this, when we use this like absolute value notation, that is referring to cardinality of a set. So when I say like this over here is saying how many elements were in the union of sets A and B.
Oh.
So that's where the 3 came from. There are 3 elements in here. And this came from, well, A had the cardinality of A was 2, and the cardinality of B was 2, so this would be 2 plus 2 is 4.
Oh, okay, I see it. Thank you.
Okay, so let me just first explain how the exam is going to be administered, since we're in this remote world, and you might not be sure how that's going to go, and you might be doing different things in different classes. So the exam is going to open up on Wednesday at 2 p.m. in Canvas, and it'll be like a PDF document like your homeworks are. I'll say that there will be a multiple choice component of the exam, which is going to be in Canvas itself. So you'll enter your answers in Canvas like you're doing with the reading quizzes. They'll all be multiple choice questions. So it should be really clear how to enter your answer. You click the choice or choices that you think are best. And so those are going to be submitted directly in a Canvas quiz and graded within Canvas quiz. And then the rest of the exam will be partial credit type of stuff on paper. So proving things or, explaining things or things like that. So the multiple choice part of the quiz, you'll have 30 minutes to complete that. And then the remaining time will be devoted to the proofs. And so from 2 to 3:15, I'm just asking that people find a nice quiet place to work, get onto Zoom like we are right now, and just turn your camera on. So just be mindful of that. If there's stuff going on in the background, then you can just put a virtual screen in the background. But I do want to make sure that everybody in the class is actually there taking the exam. And so then the written stuff you can upload into Canvas like you do with your homework, and I'll do the grading on the exam. So I'll be the only person who does the grading for the exams.
So the multiple choice opens up at 2, and then we just take that right away, and then the rest of it will be a PDF form. Do we have to print that out, or can we just like put it on a piece of paper?
Yeah, so that's right. The exam will open at 2. You want to start with the multiple choice stuff because that will close at 2:30. And then you'll have a PDF with the short answer and show your work type of problems. You don't need to print that out. You'll just need to upload your answers to those problems. Like however you've been doing it with homework, you can do it the same way on the exam. So if you're writing it up and taking a picture and creating a PDF, that's totally fine. If you have a tablet and you're writing it out, that's totally fine, whatever you prefer.
Perfect, thank you.
Mm-hmm.
How long do we have for the written portion?
Yeah, so I'll say that you have 30 minutes for the multiple choice. I don't think it should take you the full 30 minutes to do all of them. And then you have until 3:15 to finish up the proofs. So I'll just say you have 75 minutes altogether for the whole exam. Yeah, and if you have any questions during the exam, I'll be on Zoom. I might not have my camera on myself, but I'll be here watching you and checking my chat. So you're welcome to, if you have some questions during the exam, like, hey, I'm not sure what you're asking on this part, you're certainly welcome to chat me during the exam.
Will there be questions? I know that some like math classes have them like the exams in a way where it's like, you need to show me how to, like you need to actually do the proof, or like you need to show me how to do the proof, if that makes sense. So like the format to doing the proof rather than actually doing the proof? Is that how it's going to be, or are we going to be actually proving things?
You're going to be proving things, yeah. So I'll say that the multiple choice part of the exam will be, you know, similar to the reading quizzes. I'm not trying to trick you or do any sorts of things like that. So I think reviewing those questions would be good for the multiple choice stuff. And then the short answer is going to mostly be proving things. So not so much what type of proof technique is being used here, because that's more like something that can be asked in a multiple choice sort of question. But like, here's a statement, prove, is this thing true or false? And prove it, that sort of stuff.
Sounds good.
And so I think like getting ready for the multiple choice sorts of questions, yeah, look over the previous reading quizzes. I don't think there'll be anything too shocking there. As far as getting ready for the proofs, the things that I ask you, I'm not going to ask you to do any new proof techniques. We've learned all of the techniques that you're going to need to do. I'm not going to ask you to prove something that we've already done together. So don't expect to see a problem that you've already done on homework or something like that. That doesn't mean that those homeworks are not useful for you. You know, the more proofs you practice, the better you'll get at it. But just be aware that you'll have to prove statements you haven't seen before using the same techniques that we've been practicing. So like with that said, I don't think like the most useful thing is to have like a huge stack of every problem that I've ever done in this class and let me try and look through it to find that proof. You're going to be in a time situation. So I would definitely recommend like trying to get a study guide of like 1 page organized. You're welcome to use as much of your own stuff as you like. But I would suggest that it is time. So the more stuff that you can get like up here and the less stuff you need to sift through during the exam, the better place you'll be in. But during the exam, you're welcome to use your own materials. I just ask that you don't use materials created by anybody else. That means don't use stuff on the internet, don't use the textbook and things like that. Okay, question, Caden.
I have a few, sorry.
Yeah, sure.
The first one is I wanted to know, as far as like the actual writing proof stuff, can we have an idea of like how many there will be? So like we know how much time we should like generally allot to writing a proof. Like, is it going to be like a lot of them or is it just going to be like a few?
What do you think? What do you think is a fair amount of proofs to ask?
Well, if we only have 75 minutes and 30 of it's open for the quiz, but it shouldn't take us the whole time. Hopefully not too many. I mean,
yeah, so I would say some will be longer than others, but I would say you should expect about, and not the entire short answer portion is not going to just all be proofs, but I would say you should expect to have to prove, you know, 4 statements or so.
okay. And then my next question.
Yeah, and let me just say that, like, as you know, some proofs, and it's subjective, some are harder or easier than others. So I'm not going to ask you 4 of the hardest things. I'm not going to ask you 4 of the easiest things, but there'll be some that, at least by my summation, are like easier, medium, and hard.
Okay.
So like we've done tons of, what I mean by like an easy proof by this point would be like, if this thing is even, show that this thing is odd. Like we've done millions of those and they start to get some familiarity with those. But there'll be some, like with power sets, maybe that are a little bit more challenging. So there'll be a mixture of difficulty, at least that's my intention.
Cool.
Yeah.
Then my only other question was just so you just said that we can use our notes and everything. I just wanted to make sure, because on like the little exam information thing, it said we can't use like anything at all. So I just wanted to.
Where? On the exam, I sent a, here, let me open it up to make sure we're looking at the same thing.
Oh, well, I guess it specifically doesn't talk about notes. It just says like the textbook and course materials on Canvas and everything. So maybe I,
Yeah, yeah, I just want to, it's good, I just want to make, it's good to know so that everybody knows what you can and can't do. So yeah, that's kind of relating to this stuff down here. So in green, it says you can use your own notes or anything else that you put
Okay.
together. What you can't use are the internet, any of the course materials that I've made. So you can't use my solutions. If you write up
Yeah.
your own solutions, you can, and the textbook or anything like that. Yeah.
Okay, cool.
So really what the goal here is that in theory, this shouldn't be any different than if we were all in the same room. I would let you use your notes and I wouldn't let you use a textbook. So it's the same idea.
Okay, cool. I just wanted to be totally sure.
Yep. No, I think that that's exactly what I want to make sure everybody knows what they will be able to use during the exam and what they're not allowed to use. Yeah.
Thank you.
And so related to that, I did put some questions on this guide. Sorry. On the second page that are just like, I think these are good things to reflect on when you're going back and reviewing the worksheets that we've already covered. So I think that it's a little bit different the way you prepare for an exam in this class than maybe in some of the other math classes that you've taken, where you get like a practice sheet of practice problems and you kind of, know what sorts of problems you might expect. It's not different here in that you should expect to have to do direct proof, contrapositive proof. Those sorts of things are going to be used here, but I think you want to be a little mindful of like the bigger picture and not just get lost and let me just do an example and do an example and do an example. There's a balancing act there. But I did want to ask Nat, because Nat has been a student in this class and he's done well in this class. Nat, do you mind sharing any sort of study strategies that you found helpful in this class?
So I would say the only thing you need to focus right now is just learn the definition and understand them. So you need to know what is power set, what is odd number, what is intersection union, what is injective function. It is really important because the process of doing proof is first you make an assumption, your reasoning, and conclusion. So when making assumption, you need to try your best to get all the information from your assumption. And by knowing definition, you are able to interpret your assumption. I think if you can do that, you can get like 6 out of 10. Yeah, I think that's all I need to tell you right now.
Thank you, Nat.
Yeah, thank you.
Um,
I had a question.
yeah.
Should we expect to have to say at any point that in the middle of a proof, just have to say like, oh, we proved this elsewhere, so I'm not going to prove this part of it here again? I know we had to do that on the homework a couple times.
So once we've proven something in class, yeah, you're welcome to use it. Like for example, we've used the fact that like x and x squared have the same parity, and that comes up a lot. So if that's important in a proof, if you get to the point like where you need to show that x is even and you've proven that x squared is even, yeah, you can totally say that we've shown that we know the parity of x squared and x have to be the same. So if x squared is even, x has to be even. So you're welcome to use that result, but I think you do want to refer to the result that you're using, not in the sense of like this theorem number, but like we've shown that x squared and x have the same parity, and now I'm going to use it here. But if you're ever unsure on the exam, like, hey, is it cool? Can I just say this, or do I need to prove that? I'll be there, and you can chat me that, and I'll be happy to say like, you know what, you need to explain a little bit more.
Okay, thanks.
Yep. Like I won't say like, yeah, that answer is great or that answer is wrong, but I can say like, I think that you're on the right track, but you should explain a little bit more. Yeah. Kaden, do you still have more questions, or is that from, I see your hand is up.
Oh, no, that was from earlier. Sorry.
Okay, that's okay. Any other questions about the exam as far as like the format, or even if you want to, if there's anything in particular you'd like to practice before we go for today?
I have a quick question.
Yeah.
Okay, so is it okay if we like print out the exam and just write on?
Mhm.
Okay, since our cameras are going to be on, are you okay if like we get up and leave the room to go do that?
Yeah, that's okay.
Okay, I just didn't want to look sketchy while I did that.
Yeah, I mean, there's always this balancing act. It's this kind of new environment of being together but separately together, in that I don't want to get up in your business while you're taking this exam, but I do want to make sure that people are doing their own work. So there's this balancing act that I'm hoping that I'm trying to find the right place. I don't want to use proctoring software. I don't think that is too necessary for us. So I'm just going to ask that, like, yeah, as long as I can see that you're there on Zoom. If you need to step aside and go to the bathroom or something like this, that's totally fine. I realize that everybody is at home as well. So yeah, as long as it's within reason, I'm not trying to find cheaters. I just want to make sure everybody's doing their own work.
Okay, thank you.
Yep. Stephanie, yes.
So once we're done with the written portion of it and we have it submitted, do you want us to like just check out with you and be like, hey, I'm done, so I'm leaving, or can we just peace out silently?
No, you can go. I think it might be good if you do finish up early, to send me a message, and then just I can check on my end of things to make sure that your upload went well. Like usually what I do, this is what I did after your first homework assignment, is when the exam is done, I just go through and just make sure everybody's upload worked well. And so I'll put a comment to everybody that says like, thanks for your exam or something like that. And I try to do that quickly. So if there is an upload issue with someone, we find it right away, not like 3 days from now and then wonder what happened in the midst of those 3 days. So if you finish early, yeah, definitely upload it and then just send me a chat message that says I'm done. Can you just make sure it uploaded fine? And I'm happy to do that.
Okay, sounds good.
Yep.